Have you ever noticed how a straw in a glass of water looks like it's broken? It's a super simple everyday illusion, but believe it or not, behind it is a powerful piece of physics that explains everything from how your glasses work to where rainbows come from. So let's dive in.
I mean, you've totally seen this before, right? You put a perfectly straight pencil or a spoon in a glass of water, and suddenly it looks like it's got a sharp bend in it right at the surface. It's a classic trick of the eye. But it's not magic, not at all. It's all about how light behaves.
So what's the big secret? Well, the one-word answer to this mystery is refraction. It sounds kind of technical, but all it really means is that light bends. Specifically, it bends whenever it passes from one type of material into another. Like from the air into the water.
Okay, but why? Why does light bend in the first place? Well, it all boils down to one simple thing: speed. Think about it. Light is the fastest thing in the universe when it's zooming through a vacuum. But the moment it hits a different substance, like our air or water or a piece of glass, it actually has to slow down. And it's that change in speed that forces it to take a turn.
Here's a great way to picture what's happening. Imagine you're driving a little car from a smooth paved road onto, say, a patch of thick mud, and you hit it at an angle. The first wheel that hits the mud is going to slow down instantly, right? And that's going to pull the whole car, forcing it to pivot and change direction. Light does the exact same thing. A change in speed causes a change in direction.
So, we know light bends. But this isn't random. Oh no, there are very specific rules to this game. The bending is incredibly predictable. So the question is, how does a ray of light know exactly which way it's supposed to turn? Let's check it out.
Okay, it basically comes down to two simple rules. First, you have to imagine an invisible line called the normal. Just picture a line that's perfectly perpendicular at a 90-degree angle to the surface where the air and water meet. So, rule 1. When light goes from a less dense material, like air, into a denser one, like water, it bends towards that imaginary line. And rule 2, when it goes the other way, from dense to less dense, it bends away from the normal. Simple as that.
Now, when scientists say a material is denser for light, they're not talking about how heavy it is. They mean its optical density, which is a little different. And the official way we measure this is with something called the refractive index. It's basically just a number that tells us exactly how much a substance will slow light down. Let's look at some real numbers here. Air has a refractive index of pretty much exactly 1. We use that as our baseline. Water, on the other hand, is 1.33, and glass is about 1.50. You can already see the pattern, can't you? The higher the number, the more optically dense it is, the slower the light travels, and the more it's going to bend.
All right, so we get the concept and we have the basic rules. But what if we wanted to predict the exact angle of that bend? Well, for that, we need a brilliant little formula that was figured out centuries ago. It's called Snell's law, and it's the key that unlocks all the calculations.
And there it is. Now I know, an equation can look a little intimidating. But trust me, this thing is way more straightforward than it seems. It's this elegant, powerful little piece of math that acts as the engine for everything we've been talking about. Let's just break it down real quick. The N1 and N2, well, those are just the refractive indexes we just talked about. So for our example, that'd be the number for air and the number for water. The I stands for the angle of incidence. That's just the angle the light comes in at. And R is the angle of refraction, the new angle the light has after it bends. And that's it. The amazing part is, if you know any 3 of these values, you can calculate the 4th one every single time. It is incredibly precise.
Okay, so this is way more than just some formula for a physics test. Snell's law and this whole idea of refraction is happening all around us all the time. It's creating illusions, it's powering our technology, and it's even painting pictures across the sky. So let's go all the way back to our spoon. Now we know exactly why it looks bent. The light bouncing off the underwater part of the spoon has to travel from the water back out into the air to get to your eyes. And when it crosses that boundary, it bends. Your brain, though, doesn't know the light bent. It just assumes light always travels in a straight line, so it gets fooled. And hey, this is the exact same reason a swimming pool always looks way shallower than it really is.
And here's where things get really cool. We humans didn't just notice this happening, we figured out how to control it. If you wear glasses, you are literally wearing an application of Snell's law on your face. Those lenses are just perfectly shaped pieces of glass designed to bend light in just the right way to focus it perfectly on your retina. The very same idea is at the heart of every camera, every telescope, every microscope.
And for maybe the most beautiful example of all, you just have to look at the sky after a storm, a rainbow.
It's really just a massive, spectacular physics demonstration. Sunlight enters millions of tiny little raindrops floating in the air. It refracts when it goes in, reflects off the back of the drop, and then refracts again on its way out, splitting the white light into that amazing spectrum of colors.
So there you have it, one simple rule, that light changes speed when it moves through different stuff, explains everything from a simple bent spoon all the way up to a magnificent rainbow. So the next time you look through a window or at a fish in a tank, or even see the heat shimmering off a hot road in the summer, think about the journey that light is taking and how it's bending on its way to you. Now that you know the rule, what else out there do you think refraction can explain?